All right. Today we're going to talk about the magnetic force between two parallel conductors. This is 10-4. Yeah. Okay. Magnetic force between two parallel conductors. A little bit of review. Hopefully remember that we used our Biot-Savart law. To give us this exact value times I times the integral of the path of the wire times r hat, cross r hat, all over r squared. Now, hopefully you guys can kind of, there's a similarity here. Okay, it's kind of convoluted, but well, we'll show this in a bit. But there's a similarity here to our field equation. Okay, so think about our field equation and what it took. Okay, so for not Gauss's law, the one before it. Coulomb's law, yeah, or Coulomb's law, but how we get the integral for our electric field. Okay, so have that in the back of your head that there will be a similarity for this. Here's what we've got. Here's our wire. In fact, I've been drawing wire with blue, so I want to keep my. All right. Although you probably can't see that very well. Stay committed to that. So, and we know that if we have this point out here in space, relatively close to it, and we zoom in there, way in there, and let our camera freak out for a minute. Yeah, that's pretty ridiculous. Okay. Right up here we have our point. I'll call it P. All right. And as we move along a tiny distance ds, okay, we're going to have we're going to have that vector also. Now this distance is not given by r hat. This is this is the distance r, but r hat is just the direction. Yeah? Okay, so whatever that distance is. And if this is the case, because our current is in this direction, right? So we'll take, I'm going to have to zoom out here in a minute. We'll curl back around this way. Nice shot of my fingernails. And our magnetic field in the direction is coming out of the page at that spot. So current's going that way, a right-hand rule wraps around, and our magnetic field comes out of the page. Okay, and we know from the Biot-Savart law that we're going to get a magnetic field this close to a line is going to equal mu naught I over 2 pi. Well, in this case, it's going to be r, or whatever the distance is. The perpendicular, we'll call it a perpendicular distance from the wire. Okay, so what does it look like if we were to actually sit? What would it look like if we were to actually look at this from end on? And so we have, if we look at this from okay, and we're looking at it. It is shooting into our eyeball, right? So if we're looking at this, it's a face. Okay. With, of course, An epic hipster beard. Okay. Because I see all these people, like these old people are like 26, 27 that have these like big old long scraggly beards. It's like
It'll be like kissing with beards.
SMH. No. Okay. You don't have to be on the no shave list anymore. It's time to grow up. All right. So if you look at this dead on, here's the wire coming at you. And as we're moving away from the wire, at any particular point, the magnetic field actually looks like this around the wire. So if the current is coming at you, it's in this direction. Okay? If it's coming at you, and we will wrap our fingers around it, that's the direction of the magnetic field. So it's actually circular around the wire. Yeah? Okay. So in fact, that is it's a really useful method for the right hand rule is, and this is the way I learned it to begin with. There are some other ways that it is. You stick your thumb in the direction of the current, and your fingers curl in the direction of the the magnetic field. Okay. So what happens if we have two of them? Okay, we have two wires, and they're right next to each other. Okay, we have I1, and we have I2. Yeah? Okay, so if our current is going in this direction, all right, the current is going in that direction, then we have out here, right, I'm just going to start drawing dots because I don't want to have to draw circles around all of them. So here it's coming out of the page, and inside, okay, in between the two lines. No, they are currents. They are a straight line current. If we go back to the title of our lecture, Nick, we're looking at the magnetic force between two parallel conductors. So here we have two parallel conductors, and we're going to look at the magnetic force in between them.
Is that what we did last?
I'm pretty sure I haven't done this lecture yet.
Wait. Did we do is there an electric force between the two wires?
There should be an electric field in between them also. Well, wait. No. What's the electric field outside of a conductor? What's the electric field right here? Okay, it's a conductor, right? There is no electric field, right? So we're worried about magnetic field in between two parallel conductors. Good. It should. All right. So we have that, and we've got a positive out of the page here and into the page over here. All right, and we are going to look at the force that this has, and we'll separate them. We're going to separate them by a distance of A. Sorry. Okay, these guys are separated by a distance A. So, okay, the magnetic field of one out here, you know, it keeps going out. If it's over here, if it's to the left, if it's to the right of I1, the magnetic field is still going to be, on this guy, it's still going to be, in fact, this is, okay, the magnetic field that this wire is going to experience is going to be into the page because it's on this side of the wire. Okay. So this magnetic field is going to equal, if it's some distance away, mu naught I over 2 pi A, right? Any particular point on this line is going to experience this magnetic field. Yeah? So every point on the wire experiences this magnetic field if they're parallel. Okay, well, what do we know about the force? And I don't think I've actually introduced you guys to this part. The force that 2 experiences, hold on, let me make sure I'm getting this right. Right. The force that this one experiences, the force on number 2, have we talked about Phil Crosby? Okay. Phil Crosby. Okay. We've talked about the force of force equals we've talked about this, right? QV cross B, where this is the velocity of the charge. Okay. But there's the other force that has to do with the current on a wire, right? Force equals Phil Okay. So this is Phil Crosby. That isn't it though. Now you have to remember. My only problem with using Phil Crosby is you have to remember the context in which it's used, and it's rather specific. It's when you have it's finding the force from a magnetic field, okay, coming from a current. It's pretty specific.
Is it cross product like IL plus B?
This is L. It's IL cross B, so it's the length. It's the length of your current. No, it's L cross B. Yeah. Which by the way is how you're going to remember that it's L cross B is Phil Crosby. Okay. Go. Our force is going to equal. Now, mind you, this is the force. Shh. We have to keep track here. This Phil Crosby. Okay, you're going to have to get past the giggle there, Justin. This current isn't this one that's causing the magnetic field. This current is if there's a current in the magnetic field, what force does it experience? This is the force this is the force on current I2 times the length of it all right, cross B, but in this case it's going to be the magnetic field that comes from 1. All right, so now we throw that in there. They are perpendicular, so so our cross product is still is a full. The sine theta of the cross product is still 1. All right, so we're going to get I2 L mu naught I1 over 2 pi A, which is the distance between them. All right, so that's our force, and this is, what direction is this going to be? Okay, this direction is going to be towards I1, right? Current field, actually, hold on. Current, okay, I actually learned this a different way. You learned it using my palm rather than, yeah, but, so if I screw up my hand the first time. Current is in that direction, curl it into the page, where's the thumb going? That direction, which is in the negative I hat
So is it different
direction.
from what we learned?
Oh, times L. There's an L. No, that's still there. Okay.
Can we use the curve thing?
The curve thing?
Yeah, the right hand, except the palm.
Yeah. You don't have to don't use the palm. My physics teacher in high school taught me the palm direction.
Mr.
Mm.
Oh, Mr. Tortini.
No, it was that one Palestinian.
Okay. It was my physics teacher in high school, who shall remain nameless. Okay. Okay, so this is our force. This is our force on the second wire. Well, now let's find what the force is on this guy over here. Okay, well, let's work through this. B2 B2 is, we're going to do the same thing pretty much. So it's mu naught I over R over 2 pi A. Okay, and in this case, it's going to be in which direction? Ah.
Palm method. Palm.
Okay, what is it going to be over here? Current is that way. Curls. So at this guy, it's going to be. No, shoot, I'm using. Gosh darn it. Okay. The electric field coming from I2 at this point is going to be out of the page. Prove it to yourself if you have to. No.
You should add could you. English, right? Say it again? No.
Rather than filling your face with your
Could you say
trail mix, whatever you are, tune in. You obviously can't hear me over the crunch. Okay.
Oh, that add.
Okay. So the force on this guy is going to be Phil cross B. I'm glad you guys enjoy that. But this is going to be the current on 1 and the magnetic field from 2. Well, you guys can sort of see how it's going to wind up being. The force on 1 is going to equal mu naught I1 I2 again over 2 pi A, because we're just switching things up. But in this case, what's the direction?
Lecciones is
Times L. But the direction in this case is going to be
I.
in positive I. Okay, so this one is going to feel a force. F1, they are, despite my arrows to the contrary, they are equal and opposite. Oh, shouldn't they be? Because the force on 1
Cancels the other.
Oh, look, what do they obey?
Newton's third law.
Newton's third law. Okay, so this is good. This means that our physics is consistent. Okay, that we're still obeying the right rules here.
Obey.
Okay, obey. That's right, with the dude with the face and the thing.
You should
Okay.
do that for physics.
All right, so let's change our. No, it's not funny. Okay, this time we've got current in that direction and current in this direction. I1, I2. I will trust you guys to figure out that, okay, that instead, that all of the math is going to be the same, except that if our current is in this direction, right? Or I'm sorry, let's do this. If our current's in this direction, okay, and we're going to have to curl back around so that our fingers are going into the page over here, right? And then this one, if we're going in that direction, then our fingers are going into the page on this side. Okay. That if they're both going the same direction, as opposed to over here, where they were going, where the fields were in opposite direction, here they're in the same direction, we're going to get force on 2 and force on 1. Okay. Now, just an aside, imagine these are in an actual circuit. How do we get this situation? How do we get this situation in an actual circuit?
In a battery,
Okay, so let's hook up.
install battery.
Like the same.
That's the
Okay, we go this way, and then we're going to have,
that's opposite.
well, I'm going to, right, they'll both be opposite, but work with me here.
So then it's that.
This has a current in that direction. This is going to have a current in that direction. Yes?
Yes.
Yeah? So these, how would we describe these two wires?
It's like
This wire and this wire are,
opposite. I mean, it's a repel.
okay. This voltage,
Yeah.
this wire, do we have any options here? We don't have any options to go anywhere, right? That means these two wires are in series, right? Okay, what's our current going to be here? They'll be in the same
Parallel.
direction, right?
Parallel.
These are in parallel. So how do we get currents going the same? If we get currents in the same direction, okay, if they're in parallel,
They go in the same direction. Get it?
parallel conductors, if they are in parallel, what are they going to do?
Forces cancel out.
No,
I mean,
they attract.
they attract. Yeah. Oh, yeah. Mm-hmm.
Okay, so the opposite of that would be if they're in series, they're going to repel. Okay. All right. I haven't put your unit 4 or your assignment 4 on Edmodo yet.
Unit 4.
Okay. Unit 10, assignment 4. I haven't put on Edmodo yet, but I'm going to. Yeah, but this is magnetic force between two parallel conductors.